Okay, documentation again. So I've recorded one documentation video, but apparently I forgot to change the mic settings, so there was no audio. So yeah, we need to redo it again. So hello everyone, this is TK. I'm going to introduce the steering wheel design, and yeah, so basically steering wheel is for steering the vehicle, and also we have some controls on it, like the two function that we implemented on the car is the ready to drive button and the basically stop to drive button. So when the driver presses the ready to drive button, it will send out a message to the rest of the system, and like after some arrow checking, the system will turn the motor controller on. So the motor will be powered, and like when you input throttle, it will spin. And the not unready to drive button is the inverse. So when you press that, it kills the entire system. Yeah. Um, PCB design. In the PCB, we are using two microcontrollers. There's one micro basic module, which mainly is there to interface with the CAN bus, and there's also a Raspberry Pi compute module here for driving the display and basically driving the display. Providing GUI interface. Yeah. So, originally the plan is to because RPI, it has HDMI outputs, right? So we're going to hook it up directly to a LED or LCD screen driver and drive a LCD, but JLC run out of stock of these ICs, so we couldn't. Actually, these were in stock, but the shipping was the problem. So we sent out the order, the factory manufactured the board, and started the shipping, and it got lost at the custom. So we didn't receive the board that assembled by JLC. And when we're trying to solder it by ourselves, well, the pitch is too thin, so we cannot really do that. And as a final result, we're using a separate off-the-shelf compute module expansion board with the HDMI port, and we just plug a cable to the screen driver, which is also off the shelf, and drive the screen. Yeah. But anyway, I'm going to introduce you to the circuit, so it might be helpful in the future, although I think we are going to completely redo it. So firstly, there's the Pi header. Because we're only using the HDMI and also the USB and also the SPI, but for the rest of the pins we just left them floating. And yeah, so here's the data sheet of the RPI. So it has provided the, yeah, there is a official I/O expansion board for RPI compute module, so we can just take the schematic of it and just use it. So yeah, this is the RPI, and this is for the micro basic. And due to space constraints, we couldn't use the entire two header rows, so we're putting a shorter one here. and this is the LCD driver. So where this one also, it's from like Adafruit. Adafruit. Yeah, this one. And also there's like CAD file, schematic file of this one. So we just take it and copy it here. One thing to notice is that like in the Adafruit schematic file, so this is the ribbon cable connector on the board, and like it seems that they are using a single symbol here, but actually there are two components. It's a ribbon cable connector, and also there's like resistor arrays here, which we need to put it here in order for like impedance matching stuff, but basically 22 ohm resistors here. Yeah, and also the LCD uses 24 volt supply, which is converted like step up from the 5 volt supply, so we need to use this power regulator here, which is like also copied from here. Because they're like we need to use JLC PCB to do the manufacturing, and like they don't have some of these passive parts in stock, so I've tried to look up a similar spec ones and put it here, but like it's untested, so I'm not sure whether this one will work. Yeah, and also there's a I2C EEPROM on board, because I think it's mentioned in the Adafruit's documentation. So HDMI, when, yeah, here. Wait. Yeah, so the device that is like driving power, providing the HDMI video source need to know like what can the display support, basically, like what's the resolution, what's the refresh rate, all the stuff, and like this information will be stored in this I2C EEPROM, so we need to have it there. And also that's why I've also connect this I2C bus to the Raspberry Pi, so that firstly we can program the EEPROM with the correct like display metadata settings, and then we can hook up the HDMI so that it will display correctly. Yeah, so that's the LCD part. This is like the button interface, so there are several buttons, and so here the method is to use a I2C I/O expander IC to convert the bunch of button like GPIO signals into I2C bus, so that like the device can read the button status from I2C instead of like pulling the GPIO pins. And that is for I/O saving. Although we have a bunch of unused I/O here, but yeah, there's no specific reason why we use this, just for ease of debugging, I guess. Yeah, and also it can serve like kind of like a protection, because like if the button short out somehow, like the GPIO pins of the host computer device won't be destroyed, only like the chip will burn, which is kind of safe, I guess. Yeah. And here's the power stage. So this one is 12 volt to 5 volt step down regulator, which we just copy from here. Where? Here. Is it this one? Maybe. Yeah, it is this one. And there's also a 5 volt to 3.3 volt at 1 amps. Yeah, I guess so. I may change the resistor. Yeah, I've changed the resistor value so it outputs different voltage. So 5 volt in our case. Yeah, that's the main power stage. We've also added a fan controller here because like the LCD screen will heat up pretty significantly, so we want some kind of airflow inside the device. But like this IC is out of stock, so we didn't have the chance to test it. So like these are untested. And USB, we are using 3 USB ports on the board. So one is for providing, one is for like hooking up to external power supply to provide power when debugging, and the other two are connected to the Pi's USB port so that we can, for example, plug a keyboard or mouse to the Pi so we can like control it. Yeah, and so for the keyboard and mouse, I've put a USB 2.0 header there, female header, to plug the dongle. And also we've also included 2 USB Type-C connectors. And for USB Type-C standard, it's pretty complicated, but like there's a CC pin in the Type-C protocol, which we need to hook up a certain resistor value to the CC pin to indicate, firstly, whether we are sourcing the current or sinking the current, and also like what's the capability of the device. And there is a chart somewhere. Okay, not this one. Resistor. Yeah, I think it's this one. Yeah, so there's like downward facing port and upward facing port. Downward or downstream, I forgot, but it's down something. So the DFP is providing current, right? Yeah, it's for the RP resistor, so it's providing the current. It's the current source. Where was that? Yeah, here. It's on this side. So for this one, it's the current source. So we need to hook up the RP resistor to 5 volts, and here we're just using the default standard like 0.5 amps for USB 2.0. So we're hooking up like 56K resistor to 5.5 volt, 5 volt here. And for this one, because we're drawing current from the power supply, it's the other side, so RD resistor. And we need and because like we are drawing where's this back? It's right here. We're drawing like normal 5 volts from the power supply, so like this one. Yeah, 1.5 amps at 5 volt, it's definitely sufficient for us. So just a 5.1K resistor pulled to ground here. And yeah, we just put it here. And the reason why there are 2 resistors, because like Type-C connector, you can plug it in both ways, right? So in order to make it functional, independent of the facing you are plugging in, we need them to set off those resistors to make it functional. Yeah. And basically that's the schematic part. And for the PCB part, it's pretty simple. We're mainly limited by mechanical constraints, so the shape of the steering wheel. And yeah, are there anything to talk about? I'm using like default trace width here, like 0.25 millimeters. And yeah. Okay, one thing to notice is like HDMI signal. It's high-speed signal, so I will expect the signal, the length of the signal wires to match between each other. And because we're turning a 270 degree here, so we actually need to use these kind of wiggly wires things to match the length of the wire to make sure they are the same. Yeah, so that's for high-speed signal. And these are the resistor arrays. Yeah, there's not much to cover. Okay, and also because like the screen it's pulling power from the 5-volt rail, and we're stepping down from 12 volt to 5 volt and then step back up to 24 volt for the screen. So there's actually a pretty large current on the 5-volt rail, so like I'm using thicker wire for the 5-volt rail from the like step down to the step up part. So basically this part. Yeah. And that's for the PCB. And we can switch to firmware. Are there anything to talk about firmware? So the code is on GitHub or on GitLab. It's in the FEB organization and under Firm 2022. Steering wheel. Core? Yeah, source. And yeah, so the functionality of the code on Micro Basic is, firstly, it's reading the 2 buttons from the I2C bus, and like when there's button input, it transmits the CAN message to the CAN bus, so that like APPS will receive it, do some like condition checking, and then send the signal to activate RMS. So from the steering wheel side, it just needs to send out the CAN message whenever there's the button press. Yeah, so that's the actual functional part. And also because steering wheel is the only one that has a display hooked up, so we're actually also logging all of the CAN message from the CAN bus and transmit to the Pi to let it like display all the CAN messages. So the CAN filter on this node is set to like all pass. We are not filtering out anything. And like the code, it's not optimal or anything. It's just it's just reading out in a very short, limited time period. So we need to work on that. And because like CAN, we're using polling method instead of interrupt, and I think UART is also polling method. Yeah, so it's high chance that we can miss some data out. Okay, an interesting thing about UART is like So UART is a stream-like protocol. It's just you can just put stuff in and it will come out at the other end. It's like a stream. But CAN protocol actually have some like it defines framing in the CAN protocol. So like when we are transmitting or receiving, we are operating on a frame-based data. So when we want to transmit CAN message through UART, we need to define a custom protocol that will divide the UART stream into different chunks to separate out the CAN frame. And we are using this method here, which like later on I will see like rewriting the CAN library, and I found out like this is unnecessary. So firstly, how this works, it will transmit the data itself and then end the data frame with a new line character. So on the receive side, we can just read until there's a new line character and then parse the former data, knowing that it is one frame. And also, like because we are using new line character as a packet separator, we need to parse the new line character inside those data frames to other values, and like this function here is doing that, so that like we can just read until you are to receive a frame. But actually, because the CAN message is framed, so when we receive the CAN message, we already know the size of the CAN message. So actually, what we can do is we transmit a header to the UART, a fixed size header that contains information such as like CAN ID, size, frame type, all those stuff. And on the receive side, we first receive a certain size, like the size of equal to the header. So we read that in, and then we know the size of the data bits. So we just need to read that many bytes from the UART, and then it's framed. And I think that's better than this method, because like here the new line character also, and also those like parsing characters, they are not useful data, so we cannot the transmit bandwidth will be smaller due to those wasted characters. Yeah, and UART is already pretty slow. So yeah, we can improve that. And yeah, that's about this firmware. And also I have a UI part, which is like Python script running on the Raspberry Pi. So like canalize, yeah. So how this one works is like the Python code, it will set up a server, a web server, and on the RPI, and then it will open up, or like we can open up a browser, web browser, to access that server, and it will display, it will log out all the CAN messages. And the benefit of this structure is like, firstly, Python itself doesn't have very nice GUI interfaces or GUI frameworks. There's like PyQt, but that's not easy to set up, and that's not good looking either. So yeah, we can rely on the HTML front-end stack to do the GUI stuff. And also, this way we can hook up the Pi to a LAN network, and then we can, because that is a fully functional web server running on Pi, we can use other devices such as a workstation or a laptop to access the IP of the Pi and show the web browser on that device. And that's actually quite helpful. Like, we can send out the car running in the track, and as long as it's covered within the Wi-Fi range, we can just log the data over Wi-Fi in the pit area and like monitor those real-time cam messages. Yeah, so that's the idea behind this server setup. It's just server like running with, I think, using Flask. Yeah, Flask. And because we're running the server and also communicating to MicroBasic on UART at the same time, so we need threading. Yeah. And these are just like web development stuff. It's like a server, yeah. Yeah, so I think that's all about the steering wheel documentation. Okay, good. Hopefully this time I got the audio recorded. Yeah.